coordinate system which is defined by ui equal to ui hat of x1, x2, x3, and the inverse relation xi equal to I equal to 1, 2, 3. For the general curvilinear coordinate system, which need not necessarily be orthogonal, right? An orthogonal system. There are actually 9 metric coefficients. I'm not going to define them and see the significance of the metric coefficients. They may be defined as Gij. It's a matrix of metric coefficients. There are 9. I equal to 1, 2, 3. So you have G11, G12, G13, and so on. So it's a matrix of metric coefficients. Right? The matrix, we can call it G, is G11, G12, and so on. So when you have an orthogonal system, it's possible to show, you just now see from the definition of these metric coefficients, from an orthogonal system, the metric coefficient matrix will be diagonal, and we have only to consider the diagonal element. So there appears to be a very powerful way of so all of the operations that we have considered so far, the gradient, the divergence of a vector, curl of a vector, and so on. If you look at Stewart Lightfoot in the appendix, he actually calls these as H1, H2, and H3. Right? And he gives a set of formulae for some of the quantities, all of which involve vector fields, where the formula that we have derived just for the cylindrical coordinate system are actually expressed in terms of H1, H2, and H3. That in fact would be wonderful. We only have to do the derivation once, and the moment you find what the H1, H2, and H3 for a given orthogonal, this will apply only to an orthogonal, because for an arbitrary curvilinear coordinate system, the formula would probably be much more complicated because they would involve all the 9 coefficients. Right? But orthogonal, he has given a few of the formula in terms of the H1, H2, and H3. So what it means is that if you have those formula, the moment you calculate H1, H2, and H3, you have the formula for all the various operations, that we have so far derived, all in terms of H1, H2, and H3. So we don't have to rederive each and every one of them for each curvilinear coordinate system. But I didn't adopt that rule because it's not very clear how to do that for operations involving a tensor, for instance. Those expressions are not given in words to Lightfoot. It's given a reference for more such formulae, and I haven't had time to search out that reference and do that. If I had been able to do it, I would have taken that rule, so that you have all the formula for any arbitrary operation involving the gradient or anything else in terms of the metric coefficients, of which there are only 3 for the orthogonal, and then you just have to find the metric coefficient for a particular orthogonal coordinate system, and you will get all the formula in one stroke without having to do these kinds of tedious operations each and every time. But I haven't done that yet, so I didn't want to. So I didn't want to give you a limited view of just a few of the operations using that, and then again we have to do all this for each coordinate system separately. So I've taken a more tedious but certainly easy to execute method for each of the various operations that you're likely to encounter in fluid mechanics. Right? So now these metric coefficients will also come in when you're actually, for instance, suppose I have this. In this formula, this gives the mass flow rate across a control surface, let's say. Right? So we need the N. We also need what the dA is going to be. Now we have seen, for instance, I asked you to consider a rectangular volume element. We calculate the force and so on that rectangle. Or for instance, if you want to calculate N dot dA, both of these cases we need the normal as well as what the dA is going to be. Now in the rectilinear coordinate system, if you are choosing the coordinate surfaces, right, as your area element, it's very clear, right? The normal, for instance, to the 1-2 plane would be the E3, the area element would be dx1, dx2, right? Now what would it happen? For instance, if you are considering the flow across a cylindrical surface, right, of a certain radius, how would you calculate it? What would the dA be? The n we know now, the normal how to calculate for any coordinate surface. What would you have for the dA? Those can be represented from arbitrary curvilinear orthogonal coordinate systems in terms of the metric coefficients. So I am now going to give you the formula, right, without really going into details of the derivation, which you can apply to any orthogonal curvilinear coordinate system. So when you are doing the integration, you can identify a particular coordinate surface that is of relevance. Then all you have to do is to use the metric coefficients and along with the formula for the normal and the area element. So how is the metric coefficient defined? Metric coefficients are defined in terms of the tangent vectors. We've already seen that you have x dx by dui, right, will give the vector which is in a direction tangential to the u1 coordinate line, right? So now the vector coefficient dij is given by defined as the dot product of this is arbitrary for any curvilinear coordinate system, no matter if it is orthogonal or not. Clearly, you can see that in the case of the orthogonal curvilinear coordinate system, we have seen that this will give only one set of basis vectors. The other set will be given by the normal to the coordinate surfaces. So the orthogonal, the two will be proportional to each other. So if the system is orthogonal, one set of basis vectors are orthogonal, the other set will automatically be orthogonal, as we have in fact verified for the cylindrical coordinate system. So clearly for the orthogonal, we see that only T11, T22 and T33 are non-zero. D11, D22, D3 are non-zero because if I is not equal to j, then that because it's an orthogonal system, all those coefficients will be 0. So now, in terms of the these metric coefficients, right? We will now write down the so now we have the U1 equal to constant coordinate surface right. So now we have to identify what is the unit normal to the U1 equal to constant coordinate surface, right. So this would be given by dx by so n would be given, the normal to this coordinate surface would be given by I'm not defining it in terms of the tangent vector only, because they will be proportional for the orthogonal. So if you want the unit normal, this we have already calculated, right? This is what it would be. Area element corresponding to the U1 equal to constant coordinate surface, I will write as dA23. That would be square root of D22, D33, Du2, Du3. correspondence with the rectilinear Cartesian coordinate system. U1 equal to constant coordinate. So this, let's take the x. There the vector coefficients are all 1. So it's just x1 equal to x1. That's the transformation. So 1-to-1 transformation of itself, right? So x1 equal to constant would be the x23 query, right? So the normal would obviously be given by E1, right? That you have to prove. dx by du1, that's the vector, and I take the unit normal. Okay, let me check the formula. Because I want the unit normal, so that is why I am taking that. So I can call this and in fact I can, so this is the normal, so I call this as N1. This is the normal to the U1 equal to constant coordinate surface. You verify these formula for the cylindrical as well as the spherical, so that you get to know what these mean. And in fact, I can write this as the area is actually a vector which includes the magnitude of the area element, right? And also the vector which is the normal to the area. That I can write it compactly as N1. So the coefficient, so this would be 1 and 1 for the rectilinear coordinate, and you simply get dx2, dx3. The normal would be E1. So this will give you a way to translate this, right, for arbitrary coordinate surfaces, right, or arbitrary curvilinear coordinates. So U2 equal to constant surface, the normal would be given clearly by dx by du2, because it need not necessarily be orthonormal. So we want the unit normal, we have to take divided by the norm, right? And then I can write dA2 for this, I get 1 3, and that would be a 3 1 whatever you want. The square root of d3 g11, right? du1 du3. These basically represent some kind of transformation that you do when you convert integrals in one set of coordinates to that in another coordinate. These are somewhat similar to that. Constant surface would be again and dA1 2 would be square root of g11 d22 du1 du2 and 3. It gives both the value magnitude of dA, and you also get the normal in the same formula. That's what, but I've written the normal out separately because I've given you the formula, right? So the point here is that similarly, what about the volume element? Now for the volume element, because we have to, for instance, if I want to calculate the body force, I need to integrate over the volume, right? If you want to integrate over the volume, then dV is simply given by square root of d11, d22, d33, du1, du2, du3. Similarly, you can also see how the line elements, for instance, if you are integrating along the x1 line, you will simply use dx1. Now, if you want to integrate along the u1 line, right, you would not only use du1 plus the coefficient. So line elements that transform like this would be given by square root of d11 du1. This is along the square root of d2 2, du2, and square root of d3 3. So the metric coefficients actually give some kind of a transformation. These are somewhat like the Jacobian. For instance, you will clearly see that this would very much be the Jacobian of the transformation between the two coordinate systems. That we very clearly know for three-dimensional integration. The area is slightly more trickier because you're focusing only on one part of the three-dimensional space, right, across the coordinates. So these are somewhat similar to that, right? So let's now get these results for the cylindrical coordinate system, right? The cylindrical coordinate system, I have x, because this is the function I want in terms of the cylindrical coordinates, would simply be r cos phi e1 x1 e1, so it would be rc cos phi e1 plus rc sin phi e2 plus zc e3. Right? This is the x reference u1, u2, because I have to differentiate. We have already got this. So dx by du1 is actually equal to u1 is rc, right? So it would be cos phi e1 plus sin phi e2 dx by du2 is integration differentiation with respect to phi, that would be minus rc sin phi e1 plus rc cos phi e2 dx by du3 is simply equal to e3. Right? So two of them are already unit norm. Those are the ERC and EZC that we have already got. Only to get the normal, unit normal, you only need to work on this one. But what are the coefficients? D11 is 1. So dx by du1 dotted with dx by du1. So all the cross coefficients are zero because of the orthogonality property. Right? So clearly these expressions for these area items are going to be much more complicated for the general curvilinear coordinate system, which we are not really concerned about. So G11 is 1, G22 is actually, what is G22? It's actually RC squared, and G33 is again 1. Right? So clearly, for the unit normal, so this is the N1, the constant RC surface, is simply this, is equal to ERC. The constant phi surface is normal to that, right? It's actually proportional to this. So N2 is obtained by dividing this by the norm, which is RC. So the length of this is RC squared. Length squared is RC squared. The norm is just the length of the vector, which is RC. If I divide it by this, then I get E phi. This is the normal to the constant phi surface. This is, of course, I have directly calculated it as the tangent to the particular coordinate line, but the two are proportional, as we have seen. And N3 will be ZC. Now, what about the area elements? Right? So D A23. So this is the constant. One here is RC. U1. This is U1. This is U2. And this is U3. Right? So let's now look at what DA23 is. Right? The 2 is for the phi ZC. 2 and 3. Right? This is the surface of the cylinder, the constant RC surface. Right? Constant RC surface will be represented by d2 square root of, so that would be RC. Right? All the other coefficients are 1, so this would be what? D5, DZC. This is the vector. So if you want to write it as a vector, I can write this in one compact form. This representing the area element, there is no square root here. RC, D5, DZC, and the normal to that coordinate surface is automatically given by this formula as ERC. Right? This is the R, dr, d, R, d5, dz that you do with integral. The point and the reason I am expressing this is some of these can be geometrically obtained for the very familiar cylindrical and spherical. But what these formulas give, right, and the geometry is not that straightforward for arbitrary curvilinear orthogonal coordinate system, where you have analytical expression, which is more common, that you have analytical expressions for the coordinate transformations. You can easily calculate the corresponding normals to the coordinate surfaces and the magnitude of the area element very directly by calculating these metric coefficients. Right? So the generality of these formulas is what you should keep in mind. Even though we might be focusing primarily on cylindrical and spherical, there are all kinds of other coordinate systems that you might encounter, right, in your work. Right? So for all of those, we have a single formula that would give you both the normal and the area elements as well as the line elements and so on. If you're integrating along lines, which we probably unlikely to do in this course. So the same way you can write down all the other coefficients. So this would be u2 equal to constant, that is the phi, right? So the RC ZC, that is the phi equal to constant, would simply be given by du1, right? d3, so that would be the RC, right? The ZC. Coefficient that multiplied would be 1, this would be 5. And this dA1, so that's the u3 to constant surface, that is the ZC equal to constant surface. Then I can write this as RC5 is equal to D11, D12, right? So D22, that is again RC, right? DRC, D5. Right? So is this clear? And so the volume element is obviously given by RC, indicating the volume in the cylinder, right? So this would be simply RC, RC, D5, DZC. Integrate. Whenever you're integrating over the volume, the dV has to be replaced by this. Then you can integrate over the cylindrical coordinate. We'll see in the next class how these formulas, for instance, can be written for, make sure I'm putting them correctly, how they can be written for the spherical polar coordinate, which we haven't discussed at all. Right? But that will also be important because many of the problems that we solve will involve spherical polar. So I give a similar geometric interpretation of the coordinate lines and coordinate surfaces. We will also see how to calculate these vectors for the spherical polar coordinate. Right? And then we'll move on to solving some problems involving the cylindrical and spherical polar coordinate, actual flow problems. You see where these ideas are being, how these ideas are being used. Are there any questions?